Good afternoon, and thank you for joining us for the 11th webinar in the Offshore Wind series, Learning from the Experts. I am Kate McClellan-Press, Senior Project Manager with NYSERDA's Environmental Research Program, and it's my pleasure to be joined by today's expert, Dr. Drew Carey from Inspire Environmental, who will be giving a presentation on environmental considerations for fixed offshore wind foundation technologies. Before I introduce our speaker, a few reminders for our participants and some background on this webinar series. Next slide, please. First, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series will be available on NYSERDA's website at the address on this slide. All participants have been muted, and we will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts series speakers based on their expertise, not necessarily for alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, please email us at offshorewind@nyserda.ny.gov. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Dr. Drew Carey. Dr. Carey is the co-founder and CEO of Inspire Environmental. He has more than 30 years of experience addressing issues in marine science, environmental monitoring, and marine policy. Dr. Carey takes particular pride in Inspire's culture of innovation, quality, and compassion, and Inspire's commitment to workplace diversity and inclusion. He has worked on environmental assessments for offshore wind since 2009 across a wide scale of projects and topics. Dr. Carey is a recognized expert in the assessment of environmental impacts on marine ecosystems and has led offshore wind studies since 2009. Dr. Carey received his PhD from the University of St. Andrews, Scotland, and specializes in benthic ecology, sedimentology, fisheries monitoring, and marine policy. He has extensive experience in benthic site characterization, preparation of construction and operation plans, and monitoring for offshore wind energy projects. And he is currently leading marine assessments, including those on essential fish habitat, fisheries, benthic, lobster, and geological studies for the Block Island, South Fork, Sunrise, Skipjack, Ocean Wind, and Revolution wind farms for Ørsted USA offshore wind energy. And Dr. Carey has been engaged in development of marine technology and innovative applications of data visualization throughout his career. Thank you so much for joining us, and I will now hand things over to Dr. Carey.
Thanks very much, Kate. I'm going to take a pretty quick spin through the types of foundations that are used for fixed offshore wind, and also talk about some of the biological effects as we know them so far. First, I just want to give you an idea of what Inspire Environmental is, and we'll sort of move on from there. We're a marine science consulting firm. Our emphasis is measuring seafloor health. We use a system, there's a little cartoon up in the corner here. It's called a sediment profile imaging system with a plan view camera. And we collect seafloor images, both on the surface and down into the sediments. We combine that with fishery surveys, underwater acoustic measurements, and analysis. And that gives us a pretty full spectrum of the effects of any kind of offshore project on marine resources that are below the water surface. We have worked all over the world with over 300 projects, but we've actually done work on 9 US wind farms. So that's given us a range of experience of different types of projects. We have about 20 staff. We also have the world's largest collection of these types of photos. So we have over 75,000 images from all over the world. The advantage with that is that we can compare conditions at sites as they are proposed and as they are built with conditions in a lot of different environments around the world. So we're going to look at some foundation types. I'll look in a little more detail at acoustic and benthic effects. I'll spend quite a bit of time on the artificial reef effect. This is what we know the most about. And then we'll talk a little bit about things that we do seem to understand and a lot of the things that we still need to learn. So there are a wide variety of types of foundations that have been used. We're just going to focus on 4 of them here. And you'll see here, this is a survey that was recently conducted in Europe, where the majority of existing offshore wind farms are, is that over 80% of them were monopiles. Now, again, a lot of the early projects are in shallow water, used relatively small turbines, but we are seeing more projects beginning to propose gravity base. We'll talk about gravity base, and also the use of lattice jackets can be an advantage in certain circumstances. So we'll talk a little bit about the pros and cons. When floating is increasing in interest, we're not going to talk about it today. That may be a subject of future webinars. One of the things that I've learned is that there's a lot of competition in the engineering space to develop new types of foundations. So there's many ideas out there. What really counts in the end is what gets proposed and what actually gets built. So if we take a look at the sort of basics of these designs, you'll notice that in each case, there's a transition piece between the actual foundation and the turbine. So in most cases, these are painted yellow. There's ladders and platforms that allow maintenance. So these can, in practice, be fairly complicated structures, a lot of stuff going on the inside that you don't see. And in most cases, where these are placed on the seafloor, there's a protective layer of rock placed around the base of the foundation. This is called a scour protection layer, and we'll talk about that in some detail. So I put together a little bit of a matrix here for you to be able to kind of look at some of the conditions here that would suggest one type of foundation over another. There was a very recent publication from BOEM, which is linked down below there, just came out in August of this year. But things are happening so quickly that even some of the results in that report are already out of date in terms of engineering advances to push these foundations into deeper water. So the numbers you see over in the left-hand column there are based on talking to some of the engineers at a few of the developers, giving me a little bit more range than was reported there. This clearly places any of these foundations within the depths that could be proposed in the current round of leases in New York. So again, this is a good, I think, envelope of what could be considered. Running through this very quickly, and I'll go through each one in a lot more detail. Some of these have a lot to do with what we call geotechnical conditions. So what is the nature of the seafloor? They call it soil. As a marine scientist, I would call it sediment. So anything that is waterlogged is sediment as opposed to soil. But when you think of geotechnical properties, they talk in terms of soil. So those are the geotechnical conditions. Those things that are driven into the seafloor have much greater acoustic impacts. And that is one reason why these designs have evolved, is to try to avoid those acoustic impacts. A thing to really pay attention to with any of the projects, and particularly in terms of potential impact on our economy, our local coastal situation, and the whole region, is that we are facing a major surge in the need for a supply chain and thinking through the logistics of how to build these structures, marshal them, meaning getting them all together in one place, and get them out to the site safely, along with all the other vessel traffic, fishing, marine mammal activity, and all the rest. So this is a major emphasis, and it could affect which type of foundation ultimately gets chosen by a developer, because the supply chain and the logistics have major economic consequences. So it isn't as simple as saying, here's what the physical properties of the site are, water depth and soil type. You have to take into account all of these other elements, and those are still emerging. We're still determining where will these foundations be fabricated, where will they be put together, and how will they get out to these sites. So to give a little bit more of a benthic perspective, because after all, I'm a benthic ecologist, that's what I really like paying attention to. We've created this visualization of three of the more popular types, really from an undersea perspective. You can see the gravity base on the left, the monopile in the middle, and then the lattice jacket. Didn't have enough room on one picture, so here's an additional picture of a suction bucket design. The suction bucket really comes in two flavors. This is a tripod with relatively small buckets at the base of each of those legs. There's another design which is called a suction monopile. So this is essentially a very large empty can at the bottom of a single structure, and the water is pumped out of that as it's settled down on the seafloor and essentially sucks that can down into the sediment. So the way that type of structure stays up is the friction between that open bucket that is pulled down into the sediment rather than driving in piles. If we move away from installation and look at operation, there's obviously some acoustics involved in that. So underwater sound is generated by the moving parts at the very top of what's called the nacelle, which you're looking at right here in this animation. So the gearbox, the blades themselves will be transmitted down through the foundation underwater and down into the sediment. So that sound is radiated, whatever vibration is occurring up there. Thus far, it doesn't appear that the foundation type has much effect on how that noise is produced. I think we probably need more studies into terms of how it's actually transmitted into the sediment, but we don't anticipate in the water that it's that different. A lot of the new models have direct drive turbines. They take less maintenance, but they're also a little bit quieter than many of the gearboxes that have been installed previously. So to put this into a little bit of perspective, this is just modeled data, but if you had a relatively large wind farm, this is kind of a European style, only 500 meters apart, the total cumulative noise of that wind farm is roughly on the scale of a large cargo ship. Now we're going to take a little bit deeper dive through each one of these foundations, and then we'll sort of move on to the biological and ecological effects. So monopiles, which dominate the industry, they're pretty simple to construct. There's a lot of them out there, and they are generally preferred in shallower water. But as I mentioned, engineering keeps moving forward, the turbines get bigger, the foundation, the possibility of what you can do with a monopile appears to be moving towards very large structures, and they could be supported in deeper water. How much or whether you use scour protection is very dependent on water depth, the exposure, how open is it to waves and currents, and the nature of the sediments that are there. If you already have pretty coarse sediment, you may not need any scour protection. So when we look at acoustic effects of installation, you're pile driving a very large diameter cylinder as much as 200 feet into the bottom. Now I know, for instance, for CVOW, that's the Coastal Virginia project, which is what is illustrated here, that only took an hour or two. The sediments were so suitable that the pile driving just basically drove the thing right into the bottom very, very quickly. This depicts one of the monopiles 6 months after it was put into place. You'll notice there's this anode cage down here. This is sacrificial anodes so that they can monitor the steel underneath there. But that's a component that has some effect on the kind of fish that may be attracted. The other thing we know, and this is generic to all of them, is these sounds generate both pressure waves, which is what we hear, and particle motion, which is what most fish and invertebrates sense. So that pressure and particle motion is both in the water column and actually in the sediment when you're doing this pile driving. And again, we mentioned there may be some vibration due to operation. So throughout all of these, and I'll go into this in a lot more detail, we get things growing on the surface. They discharge waste down onto the scour protection layer. Things grow on that. Things begin to move onto the sediment. So that's sort of general for most of them. So this is the type of foundation that was used at Block Island Wind Farm. That's a relatively shallow location. And I think the choice of that had a lot to do with the available supply chain and the logistics of getting them out there. It's more complex to build. There's not as many of them, and they have generally been used, at least in Europe, when you get into deeper water. You may need scour protection. Block Island Wind Farm does not have scour protection except for protecting parts of the cable. But in some circumstances, you might need it for this. But you'll notice the footprint is a little bit bigger because that lattice jacket is sort of V-shape and widens out as you get to the bottom. When you do pile driving, you're driving individual small diameter solid steel pins into the seafloor. Again, it could be as much as 200 feet, depends on the water depth. So each individual pile takes less of a force, but it takes about 2.5 times as much pile driving as a monopile. So it extends over a longer period of time. Much of the same story as we talked about with the monopile, but you'll notice that there's open space inside that lattice jacket, so material can accumulate there, and it's a little bit different setting. Gravity bays have sort of come onto the scene in large part because the Empire Wind Project has proposed a gravity base here in the New York region. There's a good example in Thornton Bank in the UK of using gravity, but there's older versions as well, which have many different designs. I'm just illustrating the kind of generic bell-shaped type that is most commonly used now. Now this is hollow. It's towed out to the site with what's called a Bollard Tug. So this is a very large tug. It's pretty simple to construct, but it's big. So you need a lot of material. It's a little cheaper. And you can tow it out to the site and rest it on the seafloor. But in some cases, it's been necessary to dredge a pit on the seafloor in order to accommodate the base of this concrete structure. Then it's lowered, then it's filled with ballast, and it sits on the bottom. And in most cases, it is necessary to put scour protection because there's a very, very large diameter base. So we don't get a lot of acoustic effects during installation. There's some pumping and some settling, but not the really loud acoustic effects you might have from pile driving, but it's got a much bigger footprint on the seafloor. So then on to suction bucket. These have not yet been proposed in the US. There's a good example, a few good examples in Europe. It's a more complicated type of construction. We don't have a lot of data yet. It also needs a pretty high load-bearing soil because these cans don't go very far into the soil. So if you have good solid soil, but maybe you have bedrock underneath it, this might be a good solution. It has suction pumps that makes a certain amount of noise, but not nearly as much as pile driving. Now, when you have a single suction bucket with a monopile, you need a lot of scour protection. With these smaller, more distributed types with the lattice jacket, there may not be quite as much scour protection. I've illustrated sort of a guess really as to how much may be there. So I'm going to shift now and talk about what's called the artificial reef effect. I think many of you have probably heard about that. I'm going to dive into this in a little detail, but to entertain you, I'm going to show you a short clip of the coastal Virginia monopile so that you both get a feel for how rapidly fish are attracted to these structures. This was only 6 months after it was put into place. And you're going to get a little bit of a tour in clips as we move down that monopile to give you an actual feel for what they look like. So what we know is that all the foundation types introduce what we would call hard substrata. These are just surfaces. There you see the anode cage. And they extend through the intertidal. So those two components are really important. You have a hard surface and it extends right through the intertidal. So you have opportunities for animals that are attracted to hard surfaces to settle all the way from the intertidal all the way down. And now we see the scour protection, which is essentially a relatively flat area of boulders. You can also get animals that are going to settle on that scour protection. The combination of the structure and the things that grow on it create essentially a little island of biogeography out in the ocean. So we're going to work our way through that process. I want to start with Benthic Habitats. To me, they're sort of the starting point for cumulative effects because most anything that's introduced into the ocean eventually ends up down on the seafloor. So here you see an illustration of the two kinds of visual data that we collect, looking down at the seafloor at this lobster, and then what I call the worm's eye view, the side-looking perspective, where in this case, some mussels have settled. They're creating a richer environment. And that is illustrated by the darker sediment that you see there. So what we have is a series of 4 different sort of elements here, and I'm going to go through each one of them in a little bit more detail. So first, we know that there's a lot of modification of the bottom sediments, mostly due to organic enrichment. So the animals that are the biofilters, these suspension feeders that attach to the intertidal and on down through the water column, they're filtering plankton, zooplankton, ichthyoplankton, and that is sort of indiscriminate in some cases, but they feed on some of it, they filter a lot of that, and they discharge quite a lot of waste. And this isn't waste the way we maybe think of it, it's just organic material that is passed through one of these organisms, or it may be spat out again as they're moving along. So that creates a rain of finer material down to the seafloor, and we get finer sediments, we get more organically enriched sediments. So for instance, there's an example down here at the bottom. If you had one of these sited on a fairly coarse sediment, you would expect that it's possible over time there may be mussels down on the sediment coming from the turbine foundation itself and creating a much softer type of sediment. So part of what we need to know is all this energy that is coming from the water column and coming down to the seafloor, where's it going to go and over what distance? There's another element here I want to introduce, which is the wake and scour effects. This is both in the water column and on the seafloor. So there's a huge amount of literature about the physical effect of a cylinder in flow. And this was initiated really when people began building airplanes. What difference did it make where you put a rivet on a wing? How did it affect the nature of the flow over the wing? And we know a lot less about how this affects biological resources. Now, I actually studied a marine worm in the North Sea that took advantage of this effect and used it to enhance its ability to feed. But it was most effective when it was in very dense accumulations and sort of created a bottom reef and a lot of biodiversity. In this setting, we have large diameter cylinders widely spaced. So based on their diameter, it's really a very large distance to the next cylinder. So we really look at them individually. So it can affect larval dispersal, it can affect suspended sediment, the refuge of animals may be affected by how the flow is going around that individual cylinder. And then down on the seafloor itself, this same effect of the flow going past the cylinder can create scour. And that's why we have the scour protection layer, but it may also cause certain areas to accumulate sediment and other areas to be winnowed. Now, this is pretty similar across the foundation types, but a lattice jacket is not a big cylinder, it's a bunch of small ones, and so it has a lot less wake effects. And we expect to see more scour from gravity and big monopiles. So this is an additional component here. When we look at sort of before and after, this is both the North Atlantic, I've sort of pasted in some North Atlantic species on a North Sea image. If we look at the difference between our shallow shelf, the New York Bight in this case, with and without turbines, what you're largely going to see without the turbines is that the production in the upper water column, the primary production of phytoplankton is then grazed upon by zooplankton. Most of this falls very slowly through the water column, and a lot of it gets consumed before it gets to the bottom. We also have almost entirely a sandy bottom in the New York Bight and throughout much of the shelf of the US. So this is not a hugely food-rich environment. We have a lot of species that rely upon it, but it is a relatively slow process to get food down into those sandy sediments. When we introduce on a local scale a hard structure like this, we're essentially accelerating the flow of this energy down to the seafloor. So it could have a couple of different consequences. You're getting a lot of other animals attracted to the structure, and you're kind of speeding up the rate at which the biomass is exported down to the bottom. So we call this benthic pelagic coupling. So in other words, the pelagic production is linked to what we would call secondary production on the seafloor. And this system, which is very localized, does create a strong export of biomass down to the seafloor. So this overall enrichment creates predation, a lot of increase of predator-prey interactions, depending on what prey are available, starfish, a lot of structure-loving finfish, crabs, lobsters are attracted to these structures. In some locations, we get marine mammals and highly migratory species also coming to these sites because of the food resources. They may be feeding on the third part of that trophic level, but they're coming in for that purpose. So then there's a benthic food web down on the bottom that will respond to this energy. So in the benthic food web, we're really seeing, in every case, really, you're dealing with use of the primary production in a secondary form. So we get a lot of energy coming into the benthos. We're not exactly sure how far this extends as yet. So if we look at export, we know that these predators are going to move away. They won't necessarily spend all their time right at that site. So they're moving some of that energy they obtain from an individual foundation and they move away. There may be predators that are staying around a lot and they're going to export energy down to the benthos. We get a lot of detritus and shell litter falling off these structures, and that again, some of that doesn't really break down, but it provides a habitat. There's another process called remineralization where the benthic species turn over this material and bring it back into the water column. So what we know is that most of the studies have been on the order of 1 to 3 to 5 years. We see localized effects of only about 50 meters away from a foundation. But in Belgium, they've managed to extend these studies out 10 years, and they're seeing over time a little bit wider effects. So something beyond 200 meters. So at this point, we know that these turbines will be built at least a nautical mile apart. So that's about 1,800 meters. So we have basically a little 200-meter circle around each of them that should see some effects, and then a gap, and then another one. What we don't know at this point is beyond 10 years. There's some projects that have lasted longer, but they haven't been studied as much. So that is an important thing that we're going to need to understand. And another aspect is what's called connectivity. So we've added intertidal habitat to an area that doesn't have it. You may expand the habitat range of some species. Some of them may be native species, some of them may be non-native species. And what we know is that there are these small scale effects that we just talked about. There's some evidence in Europe of a stepping stone effect, so that these hard substrate species begin to colonize other areas nearby. Now, we know from the Block Island Wind Farm that through studies that we conducted, that there were no mussels on the hard area around the Block Island Wind Farm prior to those being put into place. Habitat was totally suitable, they just didn't happen to be there. So after those were introduced, we began finding them in tows, demersal trawls, as much as 2 miles away from the wind farms. So those habitats are gaining some species which may be of value, but they're definitely have the opportunity to change those habitats. That's providing there's hard bottom suitable for mussels in the vicinity, which is not true throughout much of the New York Bight. So then what we begin looking at are these food web dynamics. So that we know that certain species show up, but what we need to understand more than that is what is the function of those animals? How do these habitats function? What's really occurring there? What are the processes? How fast are they occurring? And what effect could that have at an ecosystem scale? It's much easier to study something very close in near proximity, get a detailed understanding of it. What's much more challenging is to expand those results beyond that 200-meter zone and try to understand, chase, in a sense, the energy to wider areas. We don't know if the effects, and again, when I think of ecological change, there are always winners and losers. So there's certain species that do better with warmer water, and there's certain species that do less well. So as we begin to change some of these localized effects, we'll have to be paying attention to that. So I'm going to try to summarize what we know. That installation of these foundations has a lot of complex logistics, very large vessels. We have to do very detailed site engineering surveys. We need to know exactly what the properties of the seafloor are and how far away is it, what the water depth, what's the risk of waves and tidal currents. The installation can have temporary impacts. There can be underwater noise, there can be a certain amount of sediment disturbance, and each of the foundation types, we sort of run through some of the advantages and challenges of each of them. There's no one size fits all here, and it's not a simple equation to determine the most suitable foundation type. There is a lot of research and development. This is such a major industry. There's so much money at risk that reducing the risk of that logistic and supply chain, reducing the noise, reducing the costs, these are all being pursued with a lot of effort to develop foundation types and installation methods that reduce all the things that I've listed here. We also know that the operation has relatively low levels of vibration and underwater noise. We know that there's a specific time horizon for this biological growth on the foundations. It starts almost instantly, and then over a period of a few years, you get a very obvious and visible growth of biological organisms on the surface, and that may continue for as much as 10 years. We know that that growth and the literal physical presence of this structure creates an artificial reef effect. And that foundation will attract certain fish over others, and it will certainly attract what we call mobile epifauna, crabs, lobsters, starfish, that sort of thing. What we don't know is the installation logistics for every future project. I don't think you can even project that at this point. We don't know the cumulative effects of installation of many, many, many foundations. I wouldn't say that right now you could pick an optimum foundation type for the New York Bight. It depends a lot on the nature of the project and all the other elements that I've discussed. We don't know how that R&D is going to change things. I mean, literally a report published this month or last month has already been superseded by some of these changes. We don't know if that low-level operation noise into the sediments really varies or whether there's any impact as a result of that. We don't really know in our environment how long the artificial reef effect sort of reaches what we would think of as an equilibrium point, so that it's not really changing that much over time. We know in the North Sea, it might be as many as 10 years. But, you know, even the Block Island wind farm is I think we're at about the 8-year mark, but we don't have longitudinal studies that would tell us a lot of change as yet. So one of the key questions is, are we actually producing more biomass, more fish, more lobsters, more crabs? Or are they just migrating to these hotspots and feeding there? And that, again, is not a simple thing to answer. We do not yet know how far away from the turbine we might see the artificial reef effect in our environment. The New York Bight is very different from the North Sea. And then there's all these other ecosystem effects. You know, primary productivity, has been a lot of speculation about these, you know, that we're reducing the phytoplankton locally, changing secondary productivity, changing larval dispersal, interrupting the picnic line, which is the layering of the ocean surface, the overall circulation, the area that's called the cold pool, the stocks of fish and shellfish. These are big, big questions that with 1 or 2 projects in place, we're not in a position to answer. We can speculate, we can model. So in terms of foundations, the site characterization surveys that are going on at this moment are the very first step in doing the foundation selection. But I'm emphasizing that the logistics and the supply chain are incredibly important and quite complicated and changing every day. Now, we don't know a lot about decommissioning. A few projects in Europe have been decommissioned. This might be a subject for a future webinar. If the habitat that is created by these structures is valuable, then there's a question of where does decommissioning fit in. There have been some proposals in the past to do what's called repowering. Use an existing foundation, put a brand new turbine, there'll be a new model coming out in the future, and use those turbine foundations and cables and reuse them. That's not in the current, you know, agreements and lease agreements, but it's something that certainly should be discussed. The last point I want to make is there's some emerging work on what's called nature-based design. This is to look at ways to enhance the habitat value of these foundations and the scour protection around them. This is a concept that's been around for a long time. You may have heard of artificial reefs being built, reef balls. So these are constructed elements that you would add to the seafloor to create refuge, to create places that animals would prefer. And then if you do that, then decommissioning has an additional piece to consider. So that's all I have. I'm certainly open to questions. I'm gonna stop sharing my screen for the moment and let Kate take over.
Thank you so much for that wonderful presentation on environmental considerations. I know that I learned a lot, and I am looking forward to this Q&A. And if If anyone has a question for Dr. Carey, please put it in the Q&A, and we'll try to get to all the questions. We do have a couple to start with. And the first one is, if there is a preferred foundation type to minimize ecological effects.
I'm sorry, could you say that again?
Sure. Is there a preferred foundation type to minimize ecological effects?
Well, I would say it depends on which winner you prefer. So in other words, if your primary concern is to minimize the temporary impact of underwater noise, then the approaches like suction bucket and gravity base clearly have an advantage in terms of underwater acoustics. But they also potentially have a much bigger footprint, a much bigger habitat change. So if you're concerned about the scale of the habitat change, then that might change the dimension. Lattice jackets have a little bit less wake effect, but you also get a larger area under them to sort of accumulate debris, which again is not necessarily a negative, it's just a different consideration.
Maybe you could follow up with just speaking to the different construction ecological impacts that aren't necessarily benthic, but may affect other marine organisms.
Okay, so during construction, there's obviously a lot of physical activity, large vessels. In general, in many cases, you're going to put a lift vessel out there, which will put piles down on the bottom, lift the vessel up out of the water so that it's stable. So that has a direct temporary effect on the bottom. There's a certain amount of noise. And then if it's pile driving, there are very high levels of noise, but there are techniques evolving, bubble curtains, literally putting a casing around it so that the noise is trapped inside. Time of year, avoiding the time of year when there might be marine mammals in the area. So those are all in the category of mitigating what we know are quite significant effects of noise. There's a certain amount of suspended sediment, a stirring up of the bottom from all those different activities. And there's just the sort of behavioral aspect of lots of vessels going back and forth. So I think those are probably the considerable ones.
Thank you. And this is also kind of following up on this theme. Do you know if the different foundation types have any influence over the benthic and pelagic communities that colonize them, or is that really determined by the siting of the project?
I think it has more to do with the surrounding habitats. So there are some projects currently proposed that are in relatively rocky habitats. So there are already harder bottoms. So let's just use Block Island as an example. Immediately adjacent to the Block Island wind farm, there is a rocky reef that is from a glacial moraine. And we studied that. We saw basically supply of animals from those rocks onto the foundations and vice versa. Seavow, which is out in sandy environment, quite a ways offshore, doesn't have that kind of adjacent habitat. So I expect to see a pretty different pattern in that. There could be some differences in the way in which animals would attach to concrete as opposed to steel.
Thanks. I think this actually gets right into the next series of questions that we've been getting on kind of all of them falling under nature-based design or ecological enhancements. And there are just questions about what kinds of designs are being considered, and if there are things like maintenance requirements that might prevent adding additional things onto the base or underwater section of the tower. Like what kinds of engineering things have to be considered with this?
Okay, so we have begun doing some work on this in collaboration with the Nature Conservancy. There's a lot of interest in this. And I guess I would put it into really three categories. The first category is the foundation itself. And at the moment, virtually every developer that we've spoke to is very reluctant to run any risk of the maintenance, the structural integrity of those foundations to attach anything to it. Now, you could put in fish hotels and things like that on the structure itself, but I think we're a long ways from the level of comfort that would allow that kind of development. In Europe, there's some thought about creating aquaculture in between the turbines. In Europe, they don't, well, at least not so much in the UK, but in the rest of Europe, fishing is not really permitted inside the wind farms. So you've got this kind of empty space. So they're considering filling it with rope aquaculture, other kinds of aquaculture, even on the seafloor. So that's a way of enhancing the habitat. There are certain kinds of habitats that when there's no seafloor disturbance of any kind, you can get reef building organisms showing up. So you could try to enhance that even between turbines. Then there's the scour protection layer itself and the surrounding seafloor. And the scour protection has to have certain engineering properties. You don't want the boulders rolling around. They need to be able to limit the scour. The idea is to do as little as needed for the highest modeled wave energy. So the developers of reef balls and other kinds of things are determining what kind of structure could they make, and generally it would be constructed out of various kinds of concrete. And you want concrete that will allow that doesn't have any contaminants in it. And then it's going to have different kinds of holes. Are you looking for refuge for lobsters, larval fish, juvenile fish, in which case the holes and the configuration would change? We would call that the focal species. So what is the species you want to enhance the habitat for? And then test the designs, make sure those concrete things don't roll around any more than the scour protection. And as long as it's on the scour protection, that it's sort of adding to that engineering value and not degrading it, I think that's the highest potential for use. Who pays for it, how it happens, how it gets permitted, that's a different set of questions. Then when we move on to cable protection layers, it's a double-edged sword because these are generally either a rock bag or what's called a concrete mattress. So it kind of looks like a chocolate bar with little squares. And these are laid over areas where the cable isn't as deep or maybe even exposed. Generally, those are made to not allow anything to grow on them. And the reason for that is these are designed to allow trawls to go over them, and any additional growth is going to interfere with, could create conflict with nets. On the other side of that double-edged sword is the notion that here we have some hard substrate. Would be nice if they were configured so that they created more habitat. Now we've seen them with lobsters hiding under them, so they obviously serve some purpose. So it could be that the cable protection that's immediately adjacent to a turbine, so the cable comes down, it has to get out to the seafloor, you can't get it fully underneath right at that spot. That's also an area where you can't really trawl. So it could be that right adjacent to the turbines, you might have a different composition of concrete to allow things to grow. So those are the three categories that I'm currently aware of.
Great. We also have a kind of series of questions on the artificial reef effect. And the first one is if there are different, if the artificial reef effect extends from different types of foundations in different ways, does that choice affect how large that artificial reef effect is?
Well, it'd be great to have a straightforward answer to that. What we know is that a lattice jacket, which is a much more open structure, has more surface area. So the more surface area, the more things you can have attached. We can tell already that there are different components to these so that, whether it's sort of shading from the current or other elements, you'll get zonation with depth, and sometimes even zonation from one turbine to another. So the different foundation types are certainly going to create a little bit different nature. What we really need to understand is the function really different? And by that I mean how much a biomass is captured and passed down to either predators or to the seafloor. Making a wild guess, I wouldn't expect there to be a measurable difference in the extent of the artificial reef effect from one foundation type to another. I think we're going to have a hard time. What I think about a lot is detecting a signal out of the noise. So as you get it some distance away from these, that signal is going to get fairly faint, like how much biomass is going out there. And so we're going to get it to a point where that signal is pretty clear, and then it's going to get lost in all the other variables that are going on, the fishing, the other activity. And so finding the absolute sort of endpoint could be quite difficult.
And we have a question that follows up on that perfectly, and kind of how do you monitor this artificial reef effect, and what are the limitations to doing that monitoring?
So I was just today editing one of the synthesis of the science reports where we're sort of trying to understand what methods could be used. So starting at the simplest, what has been conducted for rodeo and CVAL and some other things is that you basically create an inventory of the percent cover and amount of organisms that are on the foundation itself. You try to capture some understanding of the mobile species that are using it, but getting a quantitative estimate of that is quite difficult. So some of the techniques that are evolving are to use a gradient design of sampling. So maybe you have fish pots at distances from the turbine. And so these are able to capture some understanding of what's the activity of fish at different distances. The studies that have been done previously are really trying to compare the effect on finfish and lobsters of the turbines versus an area without turbines. What we're still lacking is a lot of detail of that distance piece. And then there are a variety of techniques you can use. One of them is stable isotopes. So you look at the gut contents of fish and lobsters, and we did that by just examining them under a microscope, but you can also use stable isotopes to figure out where's the biomass coming from. There's another thing called a pulse chase study, where you basically label material and follow it through the system. These are more kind of research-oriented studies, but they may give us some understanding of cause and effect. The second part is to very carefully align the changes in the benthic environment, because again, that's where we expect a lot of the reserve biomass to end up. So again, we plan to take baseline data, knowing where the turbine's going to be at a radius, or at essentially strip transects away from it at distances. And then each year after that artificial reef begins to develop, continue monitoring that. Sort of out to the point where you don't see a measurable change. Subsequent years, that margin may go out a little bit further. And then combining that with the techniques that are used by commercial and recreational fishermen for that area. So certain areas use fish pots, certain areas use gill nets. There's a variety of different techniques, but you have to figure out the spatial scale of abundance of fish in relation to that artificial reef effect.
And I think you showed how quickly the habitat changes, and how quickly fish and other organisms come into the space. Over what scale of time do you need to be studying the artificial reef effect? For how long do you expect to see those changes?
So I think you need to study them very quickly at the beginning. It's pretty interesting. The little video that I showed you is effectively there's not much in the way of food on that turbine at the time that video was collected, but there were lots and lots of fish. So this has also been seen in Europe. And so that is just fish who like to find structure and they get a certain amount of refuge from it, but they may not be feeding directly there. They may go out and do some foraging and come back. So we know that the fish are attracted even to basically a bare turbine. So then you want to begin to watch what kinds of fish are attracted as you get more growth on the turbine. You may see some differences. And at the moment, we're projecting a sort of a 1-3-5 kind of prospect, in other words, shorter term to see those changes go out at least 5 years. And at the present, we don't know if there's a lot of change beyond that, but the ongoing studies of the Block Island Wind Farm will help us understand that. So BOEM has funded additional work there. So we're well beyond 5 years there. We may get some guidance from that. It's very near shore, obviously. It's near an island, so it's a little different in what we might expect.
Great, and I think that we have time for one last quick question. And it's, given water depths and other conditions within these lease areas, is it common to use more than one foundation type for a single project?
I've never heard of it. The only way that I would think that that would occur is there's something called an offshore, service estate. It's a station that is collecting all the energy from all the turbines and feeding it into the export cable. That could be a lattice jacket where all the turbines would be monopiles, or the other way around. Because it's just a different structure. It's not under the same stresses as the turbines. But because of the logistics and the supply chain, I think it would be highly unusual to have a hybrid. Most lease areas that I've seen don't have a huge variation in depth or exposure. They're kind of designed to be somewhat similar. So unless you really sort of went off a cliff and had part of the project in one depth and part of the project in a very different depth, I wouldn't expect that. And it's even conceivable, once you have a lease area, a developer doesn't necessarily use the entire lease area. They may have multiple projects. So one could be feeding a power agreement to New Jersey, and another one could be feeding a power agreement to New York. And they may have different requirements. You could have different size turbines, so you may end up with a different foundation. I would think of those as 2 different projects.
Thank you. That's all the time that we have for questions. And thank you so much, Dr. Carey, for giving this really excellent presentation. And thank you all for joining us for this Learning from the Experts webinar. A reminder that the webinar recording and presentation slides will be available at nyserda.ny.gov/osw-webinar-series, and the address is there. Our next webinar in the series is on September 15th. Emily Shumshinia with the Regional Wildlife Science Entity and Lindy Heiss-Dunton with the Responsible Offshore Science Alliance will discuss regional wildlife and fisheries research and upcoming regional wildlife science activities. And you can register for this and future webinars through our events page at wind.ny.gov. If you have any questions or requests for future topics that you would like to hear about in this series, please email us at offshorewind@nyserda.ny.gov. Thank you again for joining us today, and see you next time.